I thought it would be interesting to compare an old fluorescent fitting that I found knocking around versus one of the modern slimline electronic ones. So what I'm going to do is I'm going to weigh these because this one's going to have a huge choke in it. Well, we call it a choke, inductor, ballast, whatever you want to call it. And it's very inefficient versus the modern electronic one, which is very lightweight and more efficient, but ultimately this one will last longer. Before we start then, let's get a set of weighing scales into the shot. These slightly quirky IKEA weighing scales. So the original heavy one, where's about the midpoint, it's about here, weighs 762 grams. If you want that in pounds, it's 1 pound and 11 ounces roughly. The electronic one, on the other hand, weighs 70 grams roughly, which equates to approximately 2.4 ounces. So there is a significant weight difference between them. Okay, what I'm going to do now, I'm going to get the tester up and I'm going to plug this into it, let it warm up, and then we can see the power readings of it, and then we'll compare it to this one and see how the efficiency goes. One moment please. So we'll start off with the traditional ballasted unit. It's an 8-watt tube and its power consumption is currently 14.8 watts. The current is 162 milliamps and the power factor is 0.37, which is fairly abysmal, but it is just a simple inductor. This is also notable for when it's powered on. I don't know if it's going to do it straight away. Also notice the earth wire dangling out here. There is no convenient earth connection in this. If I turn it off, is it going to just light immediately, or is it going to do this little warm-up thing? It's doing its warm-up thing, a couple of blinks, and then it starts. We'll discuss that in a moment. Okay, now I shall set up the other one, and we'll compare that. One moment, please. Here is the electronically ballasted tube, which lit up almost instantly. It has no earth by default, even though it's got a metal case. It is a grey import from China, and its power consumption is 8.47 watts. Current is 58 milliamps, and the power factor is 0.59. So actually better power factor theoretically than the traditional inductor. Okay, I shall unplug this now, and we shall open both these units. So let's start with the most complicated one, because they are complicated. So I shall put this down here, and we'll just focus up to a more sensible height. I shall take the tube out of it. This is one that came with a UVC tube. For obvious reasons, I didn't fancy making the video with UVC tubes. If we just squish the end off, as it's so easy to do, there are 4 wires inside. 2 of them go to the lamp cap, and 2 of them go to the pins in the back. Noting that this type of fitting has pins at this end and pins at this end that you can reach your finger in and touch while they're live. There is a little plastic cap for going over it, but it's not ideal. It's not idiot-proof. Fortunately, we're not idiots. Most of us. Sometimes we're idiots, but only in a good way. Okay, so I cut that off. I don't know if there's any other way to actually get these off. And squish this one out. Oh, it's held on by a sticky label. That's very handy. Let's get a sharp knife and slit that label. Oh, it's got lots of stuff in the label. I've never read any of that. It's got warnings in Chinese. Excellent. So if I now wiggle this and it comes out, it should slide out with the driver. Oh, it's tight. Tight. And it's all wrapped up in a plasticized card. Will it hold a charge, I wonder? I'll find out in due course. Sticky tape. This is going to be the hardest one to reverse engineer by far, because it's got the electronic driver on it. It's got... trying to get rid of the tape off the fingers here. Get off. Right now I can see... There's the capacitor that I want to... There's the capacitor that I want to short out. Note that I could use a bare metal screwdriver to do that. I will not in this instance. There's the loop through wires going through. There's the 2 to the end of the tube. There's the other ones to the other end of the tube. and the other supply. There's, I'll show you. I'll show you the circuitry once I've taken a picture of it. There's no point analysing it too much now. But let's take the other fitting apart now. It's somewhat simpler. One moment, please. Here is the other fitting. I shall pop the tube out of it. Same type of tube connection system, the push in and twist. But this time, to get the cover off, with this one, it's normally held on by the screws that hold it onto whatever surface you've mounted it on. But this would normally be the front with the clicky switch on it. Let's get this off. And what do we have inside? We've got a tam light. We've got a tam light ballast, what we'd call the choke, rated for 150 milliamps. Cost by, it says 200.35, so pretty accurate there. And then we've got the starter. The starter is very degraded in this one because it's an old one. And it's been exposed to the ultraviolet wavelengths and the blue wavelengths, and it's made the plastic on the front of the starter go all crumbly. But this, well, look at this. I'll show you the schematic of what this does and describe its operation. We can look up closer at this. We can just nibble right into it right now. Let's cut the plastic away here and pop this out so we can take a closer look at it. In a way, the modern electronic ballasts, they've become much more refined. The first ones, the first compact fluorescent lamp units, were just a bit volatile. They used to blow up. Here we go. This one has a neon-filled globe. It might be neon, it might not be neon, this one. It might be a different gas, it might be argon. It's got a bimetallic strip and then it's got a little capacitor across it. A contentious capacitor. I thought it was for noise filtering. Other people think it's for a different purpose, to help make the contacts just briefly stick together. I'm not sure about this. But I shall take pictures of these things, particularly this one, because this is the one that's going to take all the time to reverse engineer. And then we can explore circuitry together. One moment, please. Reverse engineering is complete. Let's explore. So we'll start off with the easy one first. I mean, there's quite a lot of science going on, but it still is just the easiest. The traditional fluorescent fitting has the incoming supply, the live or neutral, but usually the live goes via the inductor. It's just as long as it's in series somewhere. And then it goes through a little heating element at the end of the tube, which is coated in a thermoemissive coating. If you take a look at the ends of the tubes, can I just show you this? Can I basically just bring it up here and focus on that? Can you see that little heater in the end there? That is coated in a thermoemissive compound. Okay, let's go back down. The reason for that thermoemissive compound, the heater, is because if this was just a cold cathode tube like a neon tube with a standard electrode at each end, you get a very high voltage drop across the electrodes. That's not a problem if you're just basically smashing it with high voltage like neon signs do. But in the case of something that has to operate in 120 to 240 volt, that drop is significant. So what they do is they use these heated cathodes that have this compound on them. And initially, before the tube starts, you have to heat that up to drop the voltage that will be dropped between that and the gas. The gas inside is typically argon, but could be krypton, and it's got a little sniff of mercury vapor in it. In the case of this tube, you might even see them rolling about in there. There's little beads rolling around inside. I don't know if they'll be visible. They're very tiny. They're like sub-millimeter beads. And those are actually amalgam. They're not the raw mercury, and they contain just a small amount of mercury, and the dosing system is such they just put, in this case, 3 of these little beads in, and then when the tube heats up and the argon starts giving off a bit of heat, initially glowing purple, the mercury vapor then comes out of those that makes the tube fluoresce with the characteristic wavelengths inside that stimulate the phosphor. This is a UVC tube, the harmful type, the one you don't want to look at. But when this lights up, you see a sort of cyany blue colour, but it's emitting a lot of UVC. That's normally blocked by the glass of ordinary fluorescent tubes. This is special glass. And there's a phosphor inside. The UVC excites the phosphor, and that emits white light. That is the science behind it. Anyway, when you first start up, current flows through the inductor, through the little heater, and this is the starter. The starter looks like this. It's got 2 electrodes and a little bimetallic strip and a contact there. And what happens is that initially some current flows and this starts glowing. It glows a deep purple colour. Tried to catch it in camera. It's not very visible. I've got a couple of resistors in series, but it wasn't that bright. But it glows purple between the electrodes here, and I measured 173 volts across it. That's quite important. The glow inside gives off a bit of heat. I'm going to zoom down a bit more. It gives off a bit of heat, and that causes the bimetallic strip to bend. When it bends enough, it touches this other electrode. Now, this is where some people say the capacitor in here is just designed to give it a bit of oomph, maybe a sort of slight spark there to make it stick and make a better connection. Not sure about that. I thought it was for interference suppression. But either way, the contact touches the other side and shorts out. And when it shorts out, the full current, limited by the ballast, the choke, goes through the heater, through the starter, and through the other heater, and the ends heat up. Then, because this is now not glowing, because it shorted itself out the bimetallic strip, it cools down and it opens the circuit, and in doing so you get a slight inductive kick from the inductor here, but also because these are now hopefully warm enough, it will strike across the tube. But if it doesn't, it will start glowing again, and then you'll see that going dink, 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 dink as it's trying to light. When it finally strikes, the tube remains lit, the voltage across the tube drops below the 173 volts, typically about 90 volts, I think, across a tube, and the starter will not glow anymore, so it can't cut in and cause it to strike again. Things about the inductor. I measured its resistance and inductance, 190 ohms, 3.17 henries. It is just relying on brute force inductance to limit the current through this circuit. I also measured 162 milliamps, which I think is pretty much the current through the tube. 0.37 power factor, and when you work it out, although the actual power being dissipated for this 8-watt tube was 15 watts, that was probably 8 watts across the tube and about 7 watts in heat, because these ballasts get very hot. It's the price of, you're losing efficiency because it's very simple, and they do get hot with iron and copper losses. You did, for a while, get super efficient ones that were designed to be so efficient they didn't really heat up as much, but the downside is they were very expensive. Nobody went with them. They didn't last long. If you take into account the turbo power factor and the mains voltage, the actual power dissipation, the apparent power of this whole fixture is 39 watts. So 8-watt fluorescent tube, 39 watts apparent power, 15 watts actual power. To improve the power factor, because it was an issue with big, huge runs of fluorescent fittings, and this was common in supermarkets, you really needed the power factor correction, and yet, ironically, the capacitor gave so many problems. But the capacitor would normally just be put across the supply, or sometimes in series, to try and improve the power factor. Anything else to say here? Not really. I measured the capacitor 5.6 nanofarad. That pretty much covers it. It's very, very simple. The upside of these is they're just so reliable. They just go on forever. These ballasts, I've come across them in mercury vapor lamps where outdoor use, the whole enclosure has been flooded to the point that it's caused electrical problems. Power's tripped out. When you drain it out, the ballast is fine. It's electronics, that does not happen. Even these ballasts will last decades. The thing that finally goes wrong in them is that you may get shorted turns them, and that happens, they'll actually damage the tube because they pass too much current, because they lose their inductive effect. Okay, let's move on to the much more complicated electronic power supply. Let me show you a picture of this. And flip this page over surreptitiously off camera in readiness. These are a lot more complicated. Is this going to fit in? I shall zoom out just a tiny bit. They're a lot more complicated, they're less reliable, but they are super efficient. That's the upside. Incoming supply, we've got a bridge rectifier here with 4 1N4007 diodes. We have a smoothing capacitor, and then we have 2 transistors that have a push-pull effect on an inductor over here with a feedback transformer here, this very suspicious capacitor here, and there's 2 other capacitors. One is replacing the starter, as I'll show you in the schematic, and the other one is limiting the current on each half cycle. This one's the one that's in the starter, and that's one limiting it on each half cycle. Here's the zoom in on this area here, just so I could actually get it big enough to draw. These long, thin circuit boards are annoying because when you print out A4, you end up with a thin strip of circuit board. Because of the length, it just comes out very thin. You can't fill up the image, so to speak. But anyway, let me show you the schematic. This may take a bit more explaining. This will take a lot more explaining. Hopefully it will make sense. I shall zoom in just a little tiny bit more. Power stats for this. 58 milliamps, 0.59 power factor, 8 watt through the tube theoretically, dissipated by the tube apparently, 14 watt apparent power. So it's an improvement. It's not perfect, but it's better. However, most of the power is being dissipated in the tube with a little bit of power being dissipated by the circuitry. Here's the AC supply. Circuitry will vary slightly depending on the voltage of where you are. Here's the capacitor. In the case of Europe, it's a 400 volt death beam capacitor, 3.3 microfarads. And where do I start? Okay. Here is the current path through the tube. It goes from the positive via this capacitor, which is being charged and discharged continually by these transistors. Here are the two heaters at either end of the tube and a 3.3 nanofarad capacitor between them, which trickles current through. I think it runs at a higher frequency just before, but once it's struck, this capacitor becomes the dominant one. This is the main inductor, 5.9 millihenry. That's this big chunky transformer-like inductor. And this little one, the one that's colour-coded orange, 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 is 3 windings, 8 turns on this little toroid inductor. And then we've got 3 turns and 3 turns, all colour-coded with the wire. It's quite nice, actually. Here's how I think this one works. Unlike a previous one that I showed that had a fairly complex start circuit involving a diag and a capacitor charging up and then dumping it into the capacitor, this one uses a different approach. When it starts up, nothing is running, so theoretically, as far as I can see, current flows down through this resistor. Some current may flow through this capacitor, through this resistor here, and because this capacitor is blocking the path down to the 0 volt rail, it will charge up and you'll end up with a slight voltage bias on here. If this was like the traditional circuits that do have that pulsed start, this capacitor wouldn't be here. It would just be a link straight down to the 0 volt rail, and that would effectively just shunt through this 10 ohm resistor and the very small winding. It would stop the voltage here raising up to 0.6 volts. In this case, they want it to rise up. As soon as it reaches roughly 0.6 volts in that capacitor, that transistor turns on very gently, and at that, it starts effectively pulling the end of this circuit to the 0 volt rail. The current flows through the capacitor, through that little coupling capacitor there and the heaters, through the main inductor, through the feedback transformer. That's important because now it starts inducing current in it, and you end up with current being a increased voltage to the base of that transistor. The transistor starts turning on more, it causes an avalanche effect, and it kicks into life by giving itself more feedback and providing current through the circuit. Once the circuit is fully saturated in the sense of as much current can flow, which in the first case will be, current can't flow through the tube yet because these heaters haven't heated up yet. But instead, I think this little capacitor here will initially, because it's a smaller value than that one, much smaller, almost a tenth the value, I think this circuit will oscillate a little bit faster, and that will result in these heating up until it starts conducting, and then it finds an easier path. Some of the current will flow through that, but most of the current will flow through here, and I think at that point it will actually run at a lower frequency, because it seems to be the value of this inductor limiting current and how fast these capacitors can charge up, which determines the oscillation frequency. That would be interesting to change these values, see what happened. But when it's when the circuitry has charged as far as it can, and the current through this inductor, this little feedback inductor, drops to 0, the current then starts, basically the magnetic field starts collapsing, and it does the opposite on the other side. It actually then puts a bit of current to this base of this transistor, and these transistors then just basically oscillate backwards and forwards. We have a 5.1 ohm resistor. I don't know if that's for some current limiting factor to limit peak current, and there's also this little protection diode which provides an alternative path back, because the transformer will provide reverse polarity as well. That might also be a factor in this, I'm not sure. But it does protect partly the base against the reverse voltage, and also means this inductor can find its alternating current path, which is probably what it really is. This capacitor here, not really sure. I've seen it in other circuits as well. Is it just a stability thing to stop it operating at rogue frequencies and perhaps damaging the transistors? I don't know. Never really worked that out. If anybody knows, please let me know in the comments. The transistors are 13001. The voltage is 400 volt. The gain is just 40 to 80 and think, well, that's not much. But keep in mind that this little transformer here can actually put quite a lot of current through that because it's just a few turns. And it is effectively just the voltage of the gate, the base of the transistor, 0.6 volts it's dealing with. And the saturation voltage of these transistors is 0.5. That means the voltage goes quite low when they're fully turned on, which just results in less heat dissipation. Very common transistor used in these. I think they owe their original purpose in part of TV circuitry, but then found themselves well suited to compact fluorescent lamps, and you find them in all the classic compact fluorescent lamps. But that is it. The other thing that's worth mentioning is these heaters in the end, these heaters there, once the tube is running, there is that slight voltage drop. That's what keeps them warm. It doesn't really need that current flowing through that anymore. It's interesting to note that some early fluorescent tubes and some posh ones had an extra capacitor and a PTC thermistor. Is that right? I think it was. Yes, which initially allowed more current to flow through for a faster startup, and then the PTC would heat up, and then it would rely on this other capacitor instead. Interesting stuff. So what do we take away from this? Well, not much, because ultimately they're obsolete, aren't they? Everything's gone LED, but this is the tubes that used to outlast LED significantly. They degrade, the phosphor would degrade, but ultimately the mercury emission just remained pretty high and standard, really. Except for when the Eco Brigade came in and said, we want less mercury. And sometimes the mercury, the quantity of vapor is so low that it can actually absorb into the phosphor and the surface of the glass, or even into the amalgam again. And you end up with those tubes that just glow a sort of purple colour because all you're seeing is the carrier gas, which is not stimulating the phosphor. Same currents flowing, not much light. But ultimately, the thing that degrades in the fluorescent tubes is the phosphors and also the electrodes, the emissive coating at the end. That's something that's worth mentioning. Because the emissive coating, they do lose their efficiency over time, particularly with number of starts. If the tube's running cold, it will actually blacken the end of the tube. And that's called sputtering. And it's basically the coating is blowing off the actual electrodes. So the tubes do tend to blacken the end. Also, if you've ever turned on a fluorescent tube and it's just kept flicking all the time, that's sometimes the starter that's faulty, although sometimes the starters weld and then the ends just glow continually, just glow orange. If that's happening, change the starter soon, because it's dissipating a lot of power and heating things up more than they should. But the other thing that happens is with the starters, sometimes the starter will keep trying to start the tube because the voltage drop is increased across the end of the tube to the point it keeps firing the starter. The other thing that can happen with these is that one electrode fails faster than the other, and you can get a DC bias. And when you turn the tube on, you'll hear a loud buzz noise from the old fluorescent fittings, because the inductor in them doesn't like the DC bias, because it's basically turned into a sort of half-wave diode effect. Lots of ways they can fail, but ultimately they're reliable. They lasted a very long time before LEDs came along and started strobing and flashing uncontrollably. Yes, we snipe at LEDs there, justified snipe at LEDs. But there we have it. Fluorescent fittings, quite interesting. The electronic drivers are massively more efficient, but less reliable. It's that sort of a balancing act, but interesting to take a look at. Very interesting indeed.